Okay. Hey, everybody. All right, so here's what we're going to do. I need you to listen very carefully. When you take your EOC, there's going to be 3 different levels of problems. You got your level 1s, your level 2s, and your level 3s. Now, level 1 problems, for example, are going to be the basic ones, the simple ones. For example, which form of heat transfer deals with liquids and gases and hot things rising and cold things sinking? You should be able to tell me that's convection. Now, if you're taking your test and you're missing a majority of these level 1 questions, odds are you're going to end up being a level 1 learner, which is a beginning learner. So that's kind of where your scores are coming from. If you get most of those level 1 questions right, that odds are that you know most of your stuff, so you'll get a level 2 rating. All right. Now, for you guys to get your credit on the high school science exam, you got to be able to get a level 3. That means that not only do you have to get those level 1 questions right, you got to be able to get some of, if not many of these 2 and 3 level questions right. So the more of these you're able to get right, the better overall you're going to do. And it really comes down to this. You have to be willing to put in the time and effort and read through carefully. Okay? My big recommendation for you is this when you're taking your exam. Answer all the easy questions first. Do those first. If you see a long passage or something that's going to take some time, skip it, come back to it later. Because what you want to do is you want to maximize your time. Get all those level 1s out the way, and then focus in on your 2s and 3s. And get those questions right if you can, okay? And we're going to talk about how to do that here today. So you'll see some level 1s, you'll see some level 2s, and some level 3s. The main thing is this. There's always going to be 4 answer choices. You got to be able to tell the following. Number 1, there's going to be 2 of them that are just straight up trash. Nonsense, okay, that's dumb, I shouldn't pick that, okay? However, there's going to be 2 answer choices then that will be close. All right, 1 will be scientifically correct, 1 will be scientifically incorrect. So again, the big thing is this. Identify your 2 trash answers quickly. And then when it comes down to the 2 that are close, look at them in depth for more scientific accuracy. You'll see that here with this first one, okay? So let's look at this first problem. And like I said before, or like hopefully my instructions say, I should say, is watch these after you're done going through it. I want you guys to read through these together, okay? With a partner and try to answer them and see how you do. And then I'll go over here with you. So this is problem by problem, okay? Let's look at this first one. Which claim about a current is shown to be mathematically supported by the relationship between the voltage, the current, and the resistance? If you're looking at question 1, then what you really want to do is identify which ones are trash. Well, you looking at these equations should know that the main equation is V equals I times R. So you already know that everything in this equation is being multiplied together, okay? And that's the only operation we see. So since we have multiplication here, we know that claim A and claim B can't possibly be choices here because, again, I've got addition and subtraction there. So those are my 2 stupid choices. Then comes down to my 2 close choices here, okay? So if we're looking specifically at this, I equals V times R and I equals V divided by R. This goes to your Algebra 1 standard, which is solving for variables. So what they want you to do is take this equation and solve it for I. Find out what I is equal to. Well, to find out what I is equal to, I gotta get I by itself, right? So I need to get rid of what's hanging out with my I. And in this case, it's the R. In fact, it's times R. All right? So how do I get rid of a multiply by R? Well, very straightforwardly, I divide by R. And if I do it to one side, I do it to the other. All right? And I get I equals V divided by R. And when I look over here, do you see that answer choice anywhere? Yeah, we see it here for D. So D should be our answer. And you can see where C and D are so close, so similar. All right, but it's you looking at the scientific detail here, or in this case, the math detail, and going through the process. All right, hopefully everybody here was choosing either C or D for this problem. Let's move to the next one. Again, getting a little more difficult here, okay? All right, so a student wants to set up 2 demonstrations to show different ways that heat can be transferred from a hot plate to a thermometer. All right, demonstration 1 is set up, the thermometer is suspended as shown below. So we have a heat transfer investigation. We got a little thermometer in here inside the beaker. And we actually did some of these in class where we talked about how heat would be transferred. All right, but the main thing is this. How should the student change the setup in demonstration 2? All right, so this being demonstration 1. How should the student attempt to change in the setup for demonstration 2 to observe a single type of thermal energy transfer? And which explanation correctly describes the type of heat transfer shown in each demonstration? So you're asked to do 2 things here. All right? How do you change the setup, and then which one correctly describes the heat transfer shown in each? So, if I want to see a single type of thermal energy transfer in demonstration 2, all right, then I have to be very careful and look through these. Let's look at A, and we'll kind of evaluate which ones make sense. We'll go demonstration by demonstration. So demonstration 2, replace the water with an equal amount of sand and keep the thermometer suspended in the sand. So if I only have sand in here and the thermometer is suspended in the sand, then the only thing touching that thermometer is a solid. And solids can't do convection, and since everything's touching it, that would work for conduction, I believe, since everything's touching. Let's come down here to this. B, replace the water with an equal amount of sand and suspend the thermometer 3 centimeters above the sand. So this is the weird thing. In this case, they have the whole beaker here. They have the sand in the beaker, but they're suspending the thermometer above it. And because of that, you got sand in here where you have heat transfer coming in here through conduction, all right, through all these little heat particles, or all these sand particles are touching each other. And then when it gets here to the air, you got convection going up. So in this case, you've got 2 going on. And it's just as simple as them saying suspend the thermometer 3 centimeters above the sand. That's going to give you some convection and conduction. So therefore, B can't be the answer. Let's go down to demonstration 2 for C. Remove half of the water and place a copper plate barrier on top of the water. Replace the water above the barrier so that the water above and below does not mix. So if you got a copper plate in the middle there, what that means is you're going to have convection going on at first through the water, then it's going to touch this copper plate, all right, and get conduction going on, and then touch the water again. So you've got, again, convection and conduction. Therefore, this is not going to work. Because, again, it said to observe a single type of thermal energy transfer. And then for D, remove half of the water from the container, place the copper plate. Well, there's a copper plate in again. So this one cannot be the answer. All right, so it's just a matter of looking through. If I had to pick 2 answer choices that were close, it would be A and B here. All right, those are our 2 close answers. And so if we're looking all the way through here, C and D are not going to be the answer because we've got the copper plate. That should be fairly obvious here. But for A and B, we're going to need to look a little more in depthly and be careful because the only thing different here was suspend the thermometer above the sand or keep the thermometer suspended in the sand. And that's kind of the difference here, okay? So again, it's just looking at it more technically and in detail. All right. Yes, sir. Did you need something? I'm sorry, Machines. I'm recording something, but okay. What do you mean? You go ahead, sir. Yeah, you got it. All right. Yeah, you're good. Not a problem. As many as you need. Okay. All right. So a student wants to investigate the relationship between pressure and volume in nitrogen gas by using a pressure sensor on an airtight 25 milliliter syringe shown in the diagram. How should the student proceed with the investigation, and which graph shows what the student will likely observe? So, if you're investigating pressure and volume in something, then we're going to be dealing with P, T, and V. All right, so the first thing you should have done for this problem was write that out as soon as you see pressure and volume. All right, now, how should the student proceed with the investigation? All right, well, let's see. If we're doing pressure, temperature, and volume, the first thing I've always told you to do is, if you're messing with just pressure and volume, all right, that means that you're doing nothing to temperature. And what do we do if we're doing nothing to temperature? We keep it constant. That means we put our finger on temperature. So when I'm looking through these, I want to see that the first step here, I see keep the temperature of the gas constant. That's a good thing. We know that's a good thing because I don't want to mess with the temperature. I just want to mess with pressure and volume. So that lets me know that A is a possible choice and B is definitely not because they're increasing the temperature. I don't want to increase temperature and have that throw off my readings. I keep the temperature constant. That way, if I affect pressure or volume, then the only reason they go up or down is because of the pressure and volume, not because of the temperature. So keeping it constant means we put our finger there, right? And then we push it up or push it down. Okay, so that means I can take off step 2 here. All right, for B, B is not an answer. I look down here, C, keeping it as constant, that's good. And for D, increased temperature, so I know those 2 answers. Again, a similar situation here. 2 answers are just straight trash, and then 2 are going to be close. So let's look at A and C here to see which one's more correct. Step 3, increase the volume of the gas in the syringe and record the resulting pressure. So pull the syringe out and record the pressure. That would help me investigate pressure and volume, so that would be good. All right, so I like step 2 and I like step 3 for A. Let's come down here to C. Keep the temperature constant and push the plunger on the syringe to apply different amounts of pressure and record the resulting volume. So in other words, start squeezing it together and record the resulting volumes. This would be good for me as well because then I can tell, again, how pressure and volume are related. So both of these really work. So if step 2 and step 3 for both are possible choices here, then that means the only choice that, the only thing that could be different about them are the 2 graphs that they gave us. And this is where it comes down to your knowledge and understanding of graphs and how they work. When you're looking at 2 graphs here, all right, and you're looking for what's called an inverse relationship. Inverse relationships means that when your x increases here, your y decreases. That's an inverse relationship. A direct relationship would be like this one, where the x increases and the y increases, and you get a positive slope. So what we should see here is a definite negative slope. However, since we're dealing with pressure and volume and things are a little more complicated, the graph that we're going to choose here, if you look at both A and B, or excuse me, A and C here, they both definitely go down. But only one of these makes any sense, and that's this one on top. Because as you start to go down, right, you can only get the volume so low, right? It should never go to 0. In this case, you get the volume going all the way down to 0. So therefore that graph doesn't work. This is more of an exponential decay function here. And so you can see that decreasing here, getting close to 0 but never quite getting there. This is a better choice for an inverse graph, all right? And so that's the one that we're going to choose here on this. So A is the correct answer because of that, okay? All right, moving on down. 4 students each prepare a cup of coffee. The students use similar amounts of brewed coffee, sugar, and cold milk. The table describes each student's method of dissolving the sugar in the coffee. So, which student uses the method that will dissolve it fastest? Well, we should know from dissolving things, we want to see, for sugar, a solid, high temperatures, and we want to see lots of agitation in the surface area. Okay, so let's take a look. Add sugar to hot coffee, then adds cold milk. Add sugar to hot coffee and stirs, sugar, we got hot coffee, we got stirring, and then adds cold milk. Adds cold milk to hot coffee, then adds sugar, and then adds cold milk to hot coffee and adds sugar. So if we add cold milk to hot coffee, that's going to lower the temperature. So both of these are my 2 trash choices because I don't want to make it colder and then add sugar. I want to make sure it's hot before I add the sugar. So that should leave me with student 1 and student 2 as my only possible choices. And then again, it's you knowing your science. What's the only thing different here? Well, hot coffee, but this one says stirs. So that should be a clear number 2 there, okay? Again, knocking it down to your 2 answer choices that are close, and then using the most scientific knowledge that you can for it, all right? Metals in group 1 of the periodic table most commonly form which type of ion? Well, we should know that oxidation gives us ions. That's where we get our, that's what we get from our song. And so group 1, we should know what kind of ion it forms. We'll look at oxidation numbers, and we see that it's this one, all right? Group 1 plus 1, because they all want to lose that electron to become more like noble gases. Question 6. Use this chemical equation to answer the following question. What coefficient of KCl will balance the equation? Well, like anything else, I write these little guys out and I figure out how much of each I need. So we got copper, sulfur, potassium, and chlorine. Copper, sulfur, potassium, and chlorine. I keep tabs on everything. On the left side, I got 1, 1, 1, 1. On the right side, I have 1 copper, 2 chlorines, 2 potassiums, and 1 sulfur. So I want to bring the lower side up. So copper's good, sulfur's good. Let's get potassium here first. Bring the low side up. So I'm going to put a 2 here. And that 2 will distribute to both of those and give me 2 Ks and 2 Cls, balancing everything, meaning that 2 should work. So the past 2 questions have been level 1s. These are ones that you should be getting right. If you're not, it means you need a whole lot more practice before tomorrow. Or excuse me, before Thursday, okay? That should tell you something. Get your level 1s right. All right, level 2s and 3s are understandable. Now, a scientist is measuring the mass of 2 boron atoms. One atom has a mass of 10 units, the other atom has a mass of 11 units. This model is of a boron atom with a mass of 11 units. And we should know it has a mass of 11 because we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 particles, or excuse me, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 particles in the nucleus. We know electrons don't count because they are too small. Therefore, they have no mass. Now, when we're looking at this, it asks which subatomic particle needs to be removed to represent a boron atom with a mass of 10 units. So I need to remove some mass here to drop it from 11 to 10. So I need to remove 1 particle, all right? But what particle? Because they say that they want a boron atom. So if they want it to be boron, that means that I have to remove a neutron. I have to remove a neutron because if I remove a proton, I'm going to change the identity. It will no longer be boron. All right? So if I remove a neutron, that will still leave me with boron, and it will make it boron 10 because I'll have 10 particles on the inside. If I remove an electron, it would make it an ion, and I don't want ions, and they're not going to affect the mass anyways. Isotopes, all right, have the same numbers of protons, different numbers of neutrons, and that's what we see here, okay? All right, so I've removed particle N. Now, the half-life of cadmium-109 is 464 days. A scientist measures 256 grams. Approximately how many grams of cadmium would remain after 1,392 days? Okay, so here's our half-life problem. This is a level 1, to be perfectly frank. You should be able to do this. I know the numbers are complex, but remember, half-life is a time. How long it takes to be reduced by half, all right? So we always start out with our starting amount. I gotta know that. So what's the starting amount here? A scientist measures up 256 gram sample. How many grams will remain after that much time? So that's my start, 256. And it's asking how much will be left at the end after 1,392 days. So there's my total time. I have to take 1,392 days, and the half-life is 464. I know that's the half-life because it's the smaller time. Half-life is the smaller time, total time is the bigger time there. But anyways, let's start doing the half-life, which is reducing it by half. 256 by half is 128, and that takes 464 days. So it looks like I'm probably going to need about 3 half-lives here. Let's see. 128 becomes 64. That's another 464 for a total of 928. And then we take another one, and we get 32, and that takes another 464. And if you add these 3 times up, 464, 464, 464, you get 1392, which means we should have 32 grams remaining at the end. Okay? All right. Next up. Oh, my Lord. Okay. Where are you? There we go. The elements neon and argon are not reactive. Which hypothesis best explains this? Oh, we should know that neon and argon are all the way on the right side of our periodic table in the group called the noble gases. And noble gases do not react. All right, and they don't react because they are stable. All right, they have all their valence electrons. So if we look here, they are stable. All right, you do find them on Earth. We've got helium in there. That's on Earth. They tend to give up all their valence electrons easily. No, they don't. They're noble gases. They're above and beyond those kinds of things. All right, so it can't be any of these 3. All right, and so that leaves us here. The maximum possible number of electrons in their outermost shell. Yes, we know that's why things bond, is to be more like a noble gas, to gain the full set of electrons in their outermost shell. So that's a D. So again, this is another level 1 question. This is likely what you're going to see on the test. Level 1s, level 2s, and the occasional level 3. So let's look at this level 2 problem here. Or excuse me, this is level 1. Pretty straightforward. A group of students proposed 4 different models to show the fusion of hydrogen to form helium. So, taking hydrogen to form helium. Well, we know what principle and process this is. All right, this is fusion. So which of these shows fusion going on? Well, you got to look at this. They tell you in the key here, protons and neutrons. So if I'm looking through, I know it can't be C because there's nothing being fused there. I know it can't be D because there's nothing being fused there. There's no 2 things coming together. That leaves me with A and B. Now, the end result has to be helium. Helium has 2 protons and 2 neutrons. So if I'm looking through here, the only one with 2 protons and 2 neutrons, right, is A. Over here, they all break apart into separate parts. So I got some hydrogen and then some neutrons here. And that's not what I want. So it comes down to your knowledge and understanding of how this works. See, we have tritium and deuterium coming together. This is the model you've seen over and over again, and we've drawn a number of times. Make sure you know it and how it works. Okay, so A is going to be the right answer there. And again, it should make helium. That's not helium, all right? Your 2 trash answers, 2 close answers, and then the one that's scientifically weird. That one you don't count, so A. All right, a student is modeling the fission of a uranium nuclei. The student started with the model and a diagram. This is your level 2 I was trying to talk about earlier. So, which 2 particles should the student add to the right-hand side of the model to complete the fission reaction? So in this case, you've got the neutron coming in, and it's going to make this thing break apart. The key here is keeping conservation of mass. If I have a certain number of protons and a certain number of neutrons, right, then, it's now 144 because you added 1, I should have a total of 136 particles, not 136, 176 particles all together. That's not even right. Is that right? I don't even know what I'm doing. 92 plus 144, 6, 3, 1, 236. So you should have a certain number of protons and a certain number of neutrons. Let's just focus on that then, since I can't seem to add. All right, so let's come over here to this. Which two particles could I add? Well, I want 92 protons. If you remember from class, we talked about this often enough, we know that you need krypton and barium. Those are going to be our two answer choices because we've done this often enough. And if you don't happen to know that, well, let's look through here. If I add anything else, I need exactly 92 protons, I believe, right? So let's look at some of these other ones. If I chose strontium, which is 38, and I chose plutonium, which is 94, if you add these up, well, that doesn't add up to 92 protons, all right? So that's not going to work. Let's try strontium, 38 protons, and let's try barium, 56 protons. Well, that's going to give me 4, 1, 9. That's too many, 94. The only two that you can add together here are these two. All right, so what should the students add to the right side of the model? We should add krypton and barium because they're going to be the particles in here. And it's the only ones that mathematically fit. Or if you just remember, uranium splits into krypton and barium, you should be good. All right, so that's A and D, I believe. All right, and yeah. Okay, moving it down. A student is modeling the units of formula for aluminum sulfide using the spheres below to represent them. Which one shows a stable ionic bond for aluminum sulfide? Well, again, this is a level 1 question. This is simple. I know it might be pushed to a level 2 because they're showing the models here, but it's really straightforward. Aluminum is +3. Sulfur is -2. Those are their oxidation numbers. So what do? We swap them. So we get Al2S3. Well, the only one with that is B. But if we don't know that and we just look through, this shows the oxidation number of sulfur is -1. Well, we know sulfur is in the same row as oxygen, and that's got an oxidation number of 2. So this one can't be the answer. Again, -1. This one can't be the answer. -3 for sulfur over here, and this one can't be the answer. There's many ways to check your work. You should know your science well enough by now. Just double check and make sure. Again, your answer choice is the most scientifically correct. If you do that, you'll always get them right. Okay? All right, let's move it on down. Use this chemical equation to answer the question. What coefficients will work to show that matter is conserved? Well, we got iron and we got oxygen. We got 1 iron, 2 oxygens, and we got 2 irons, and we have 3 oxygens. So, the reality is this. If I ever have a situation like this in a chemical equation where I have even and an odd, my recommendation to you was double the odd. Okay, so take this 3. I know you got the 2 and the 1 with iron, but to be honest, we know this is what it's going to come down to with the 2 and the 3. So let's double this first. All right, if I do that, that will give me 4 irons, and it will give me 6 oxygens. Right, when we distribute it through. So from here, all I got to do is look back over here this side of the equation and balance it. So now let's bring our irons up. See, now it's doable. I have even numbers. So let's bring our iron up, put a 4 here. All right, and then our oxygen. What can we do there? Well, a 3 times 2 is 6. And that will balance it out. So we get a 4, 3, and a 2. All right? This is doable. You guys should be good at balancing equations. I've seen you do it. You're all capable of it. Make sure you're getting those right, please. All right? Just double check your work. It doesn't take too long. Now, the solubility curve for potassium nitrate is shown below. According to the graph, what's the maximum KNO3 that would dissolve at 60 degrees? Well, we know this line represents the maximum at that temperature. That's the solubility curve, right? How much will be in there to make it saturated? So, if I'm looking at this, what would the maximum amount KNO3 that would dissolve at 60 degrees be? So I go to 60 degrees, and I go up, and I end up at this number, somewhere between 100 and 150. So let's say approximately 110 degrees. All right? 110 grams. So we know we can cross out A and C, but let's look at our answer choices now. They put extra in here. It could be B or D. So it says here, increased temperatures lead to an increase in solubility, or increased temperatures lead to a decrease in solubility. So which one of these is true? Well, let's look back at the graph. And in the graph, we see as temperature goes up on the X value, the solubility goes up. Therefore, if you increase in temperature, you'll get an increase in solubility. That's for a solid, and that's what we're dealing with here. If you're looking right here, a decrease in solubility would be a gas, and that would look the opposite. So that would look like this. All right, that would be a gas. Decreasing, as temperature increases, solubility decreases. So anyways, the answer choice here is B. Okay? Moving on down to 15. A student plans to investigate how different factors affect the dissolving rate of certain mass of potassium chloride in water. The student will test a different variable in each investigation: the diameter of crystals in millimeters, the temperature of solution in degrees, and agitation of the solution. The first table shows the details. This is your level 3. So if you want to get the top score over 4, you have to be able to break down questions like this. So as soon as you see we're talking about dissolving rates, you know, okay, if I'm dealing with a solid, all right, I want increased temp, I want increased surface area, and I want lots of agitation. All right? If I'm dealing with a gas, it's different. But since we see the word crystals here, that's what I'm looking for. I'm going to look for this information in here the whole time. All right? So let's look at their investigation and their data table here. The first table shows details and predictions for investigation 1. So trial number 1, trial number 2. If we look, temperature stays the same, stirring stays the same. The only thing that changes is the diameter of the crystal. So they're taking one that's 1, right, and they're doubling it. All right, and we know that if you make it bigger, you are decreasing the surface area, right? Making something bigger like this decreases the surface area because you get more volume in the middle. So what would we expect here from this? Well, if I increase the diameter of the crystal, I'm decreasing surface area, all right, which means that it's going to make it harder to dissolve because I want more surface area. So if I have less, that means the dissolving time is going to go up. So let's take a look here at the answer choices. The question: based on the predicted dissolving times for trials 1, 3, and 4, which statement contains the best prediction for trial number 2? So, in the case of dissolving time for trial number 2, that's this guy right here, the question mark. All right, I would expect that if it took 20 minutes with all this the same, all right, same temperature and no stirring, and I've increased the diameter, I have less surface area, I should expect it to be more. So if I look down here, we know it won't be the same. We definitely know it won't be less. We know it won't be the same as an increase in the diameter, so the only choice is D. Because the larger diameter of the crystals decreases the total surface area, increasing the length of exposure to the solvent. All right? So this is exactly what we're talking about here, right? Decreasing the total surface area. You'll know your answer is right because all the signs in it will be right. That's the key. Know your science, make sure all of it matches up. So we end up with D here. Moving it down. How should a student design investigation 3 to finish testing the factors affecting the dissolving rate? Well, let's go back up to, let's just say investigation 3. Okay, so, and for investigation 3, what could we do to finish testing factors? So far they've dealt with surface area, right? And I believe that this one down here dealt with temperature. So they did an investigation of the diameter, right? Increasing the diameter. They did an investigation with temperature, increasing the temperature, increasing the dissolving rate. That should make sense. Higher temperatures, faster dissolving for solids. But what's the only one left to do? Stirring or agitation. See? No change in stirring. So what we should do here is we'll keep this the same, we'll keep the temperature the same, and all we'll do is we'll fix the stirring. And again, it's about limiting your variables. So you want to keep as many things the same as you can and only change that one thing. So let's come down here to this and see if we can find something that does that. That keeps the diameter of the crystals the same, keeps the temperature the same, and only changes stirring. And that would be B. Okay? Now, if this one was a struggle for you to do on your own, it should make sense hopefully after going over what they're looking for here. All right? They're looking for those 3 key features: surface area, temperature, and agitation. As long as you know those things, you'll know what they're looking for. Okay? So in this case, again, to finish testing the factors that affect dissolving, they already did 2 tests, one on diameter, one on temperature, so the only one left is stirring. All right, bring it down here. A student sets up an investigation on the motion of a battery-powered toy car. The student uses a machine with a vibrating pin that makes a mark every 0.1 second on a long, narrow piece of tape or paper called ticker tape. This is that ticker tape card that we were thinking about. Let me just make sure that my video is still recording. And we are good. Gucci. Okay. Now, steps 1 and 2 are shown. Attach one end of the ticker tape to the toy car so the rest of the ticker tape is on the spool. Release the car so it moves away from the machine. The student conducts the first 2 steps and the ticker tape for notification is shown. So start, dots close together, and then they spread out, and then they stay the same for a little bit. So, which action should the student take in step 3 to determine the speed of the car? All right, and which analysis of the speed of the car is correct? So, how do you determine the speed of a car? Well, easy enough. That is distance divided by time. That's how you determine the speed of a car. All right, so we need a distance, we need a time, so I guess they can measure these distances, right? And we know that this makes a mark every 0.1 second. All right, so we know our time, and we can calculate the distance from those little marks. All right, and then which analysis is correct? So then you got to analyze this. So let's look. Count the number of dots on the ticker tape. Will that give us distance over time? Probably not. So let's take that out. That's crazy. B, I should say. Measure the distance between each successive dot on the ticker tape. That would help. All right, so let's say we like that because we get some distance here. Count the total number of dots. Again, no, that's crazy. Counting the dots doesn't tell me the distance. I need distance. So that leaves me with only B and D here as my 2 possible options. Okay, so let's look at the analysis. That's the thing. That's how we're going to tell that they're different. We have the same thing on both. Let's look at the analysis. The speed decreased at first, then became constant, or the speed increased at first and then became constant. So if we look here, same distance, same time, same speed, right? But let's look here. At first, they were close together. And if they're close together, that means the distance is small. If I have a low distance, a small distance, in a certain amount of time, that means the speed is pretty slow, right? So at first, very little distance means very little speed. And then the more distance we have between these, the more speed. So as we can see here, this thing is slowly accelerating. So that gives me D as the only choice it could be. Okay? All right. Rolling this on through. To investigate Newton's second law of motion. As soon as you see second law of motion, you go ahead and write this out on your scratch paper there. A student used a motion sensor and a spring scale to measure the force acting on the lead block as it was pulled in the direction of the arrow, so it's pulled this way, across the top of the table, and a diagram of the setup is shown. We've used these before in class. All right, the N stands for force, the G there stands for grams. So we can see here, as we pull it, we can see the newtons here has changed from 0 all the way to 1.5. So 1.5 newtons, and we know that's our force. So I'm just going to go ahead and plug that into my little equation here. And we know we got 0.5 kilograms there. So I'll put that in for mass. There's my force, there's my mass in my equation. I haven't even looked at the problem yet, but I'm just thinking ahead, right? What could they ask about? Well, Newton's second law, they gave me force, they gave me mass, so I'll have to look for acceleration some kind of way. Let's see. The student measured a force of 1.5 newtons acting on the lead block. The student expected the block to accelerate in the same direction as the arrow. However,